I see EPS as the radius, how far I'll look around each data point to find its neighbors. A larger EPS means I'll cast a wider net, potentially grouping points together that might have been separate with a smaller radius. Think of it like this. A wider search radius makes it easier for clusters to merge. This tells me how many points need to be huddled together in that EPS radius to officially form a cluster. A high MINSAMPLES means I need a really dense crowd to call it a cluster. Otherwise, I'll label those lonely points as noise. A low MINSAMPLES makes it easier for points to form clusters, even if they're not tightly packed together. I'm essentially setting a density threshold. I understand this is a quiz about how changing the EPS and MINSAMPLES parameters affect the DBSCAN clustering results. We'll analyze the impact on the number of clusters I get and how many data points are classified as noise. If I increase the EPS, I'm widening my search radius. Therefore, more points will be considered neighbors, and existing clusters are more likely to merge. Fewer clusters will result. That's a correct statement. By requiring more points to form a cluster, MINSAMPLES, I'm making the clustering criteria more stringent. This leads to fewer clusters because it's harder to meet the density requirement. This is also correct. If I shrink the search radius, EPS, it becomes tougher for points to find enough neighbors to join a cluster, resulting in more points being labeled as noise because they fail to meet the density threshold. This makes sense, right? By lowering the minimum number of points needed for a cluster, it becomes significantly easier to form clusters even with sparse data, thus leaving fewer points classified as noise. This is also completely correct. I'm analyzing the possible effects of changing the DBSCAN parameters, EPS and MINSAMPLES, on the number of clusters and noise points. I'll determine which statements accurately describe these effects. Remember, DBSCAN stands for Density-Based Spatial Clustering of Applications with Noise. It's a clustering algorithm that groups together data points that are close to each other based on density. I am looking at how changes to the radius, EPS, and the minimum number of points to form a cluster, MINSAMPLES, influence the results. Let's dive in. If I decrease EPS, I'm shrinking the radius around each data point. This means it's harder for points to be considered neighbors and thus be included in a cluster. Consequently, I expect more points to be left out, classifying them as noise points. Think of it like this. If I'm looking for friends within a smaller radius, I'm going to have fewer friends, and more people will be lonely, noise points. Let's reduce the minimum number of points needed for a cluster, MINSAMPLES. Now, it's easier to form clusters. Even small groups of points can become clusters, leaving fewer points out in the cold. Less lonely points mean fewer noise points. I increase the minimum number of points required to form a cluster, MINSAMPLES. Now, it's tougher to satisfy the conditions for creating a cluster. I expect that fewer clusters will be formed because it's harder for groups to meet the higher density requirements. I'm increasing the radius, EPS. This means I am widening the search area around each point for potential neighbors. Therefore, smaller, nearby clusters tend to merge into bigger ones. The overall result will be a decrease in the total number of clusters. It's like expanding the area where you look for your friends. You'll find larger groups and fewer individual groups. This section's title simply tells us that we'll be examining how changes to the epsilon, EPS, and minimum samples, min_samples, parameters in the DBSCAN algorithm affect clustering results. It's like looking at the knobs on a sound system. How do you tweak them to get the best sound? This question sets up the challenge. We need to understand how tweaking the parameters, the radius for searching for neighbors, EPS, and the minimum number of points needed for a cluster, min_samples, changes the final clusters that DBSCAN creates. Let's dive into it. I'd say this is true. Imagine increasing the radius, EPS, You're essentially giving points more chances to connect. Smaller, distinct clusters are now more likely to merge into larger ones. Therefore, you'll end up with fewer clusters. I agree with this statement too. Shrinking the radius, EPS, makes it harder for points to be considered neighbors. This makes it more difficult for them to join a cluster. So, more points are likely left unclustered, becoming noise. Absolutely. Raising the minimum number of points needed, min_samples, for a cluster makes it harder to form a cluster in the first place. Fewer clusters will satisfy this stricter condition. This makes sense. By lowering the number of points required for a cluster, min_samples, it becomes easier for points to be included in existing clusters. This leaves fewer points classified as noise, because more points can get easily clustered. This simply indicates that the previous statements, A, B, C, and D, are the options we evaluate to get to the final answer. To see which ones are true about DBSCAN's behavior when we adjust EPS and min_samples. I'm analyzing the effects of changing the parameters in the DBSCAN algorithm, a powerful tool for clustering data points. It's all about understanding how the radius around data points, EPS, and the minimum number of points needed to form a cluster, min_samples, affect the final results. This is crucial for getting meaningful clusters from your data. This question is asking you to think critically about how tweaking those two key parameters EPS and min_samples directly impact the way DBSCAN groups your data points. We'll explore how changes in these settings lead to different numbers of clusters and amounts of noise points. It's like tuning a radio, small adjustments make big differences. I see this statement as true. If you increase EPS, the radius to search for neighbors, you're widening the net. This means more points will be considered as neighbors, potentially merging smaller clusters into larger ones, thus reducing the overall number of clusters. Again, I agree with this statement. A smaller EPS shrinks the search radius. Fewer points will be considered neighbors. This makes it harder to satisfy the density condition, leading to more points not being part of any cluster, resulting in more noise points. I find this one to be true as well. Increasing min_samples, the minimum points to form a cluster, raises the bar for cluster formation. It's like making the criteria for club membership stricter. Fewer groups will form, leaving more points unclustered. And, this statement is also true. Lowering min_samples, lowers the hurdle for creating a cluster. More points will meet the requirement, leading to fewer noise points, because more points will be absorbed into existing clusters. I'm referring to the epsilon parameter in the DBSCAN algorithm. It is the radius that defines the neighborhood around each data point for finding neighboring points. Again, this is the epsilon parameter. It determines the size of the neighborhood around a data point that DBSCAN considers for clustering. This refers to the minimum number of data points required to form a dense cluster in DBSCAN. A higher number means fewer, denser clusters. Once more, I'm talking about the minimum number of points needed to form a cluster. This parameter directly influences the density threshold for cluster formation within DBSCAN. This phrase simply states the topic. We're examining how changing the parameters of the DBSCAN algorithm affects the results. It's a clear and concise title for the section. This introduces the multiple-choice question about DBSCAN's behavior given changes to its EPS and min_samples parameters. I'll be helping you understand the question and analyze the impact of these parameter changes. This sets the stage. We're using the DBSCAN algorithm which groups data points based on their density. EPS, epsilon, defines the radius around a point to look for neighbors, and min_samples specifies how many neighbors a point must have to be considered a core point of a cluster. We're starting with EPS equals 0.5 and min_samples equals 5. This information is crucial to understand the context of the questions following. This statement is exploring the effect of increasing the radius, EPS*, used to find neighboring points. I predict that a larger radius will cause more points to be considered neighbors, leading to fewer, larger clusters. Here, we're looking at what happens when we shrink the radius, EPS*. I believe that a smaller radius will make it harder to group points together, resulting in more points being identified as outliers, noise, because they won't meet the criteria to belong to any cluster. Now let's see how altering the minimum number of points, *min_samples*, needed for a cluster affects the results. I think if we require more points to form a cluster, the clusters formed will be fewer. Finally, we'll examine the outcome when reducing the minimum number of points. I anticipate that lowering the threshold will mean that more groups will reach the minimum needed to be a cluster, reducing the number of points left ungrouped as noise. This section's title simply tells us that the focus is on how changes to the parameters in the DBSCAN algorithm affect the results. DBSCAN, or Density-Based Spatial Clustering of Applications with Noise, is a clustering algorithm. We'll explore how the parameters, EPS, and min_samples, influence its behavior. This question is the core of the problem. We need to understand how adjusting the EPS, radius, and min_samples, minimum points in a cluster, parameters change the number of clusters DBSCAN finds and the number of data points it labels as noise. Let's dive in. I think this statement is true. If you increase EPS, you're widening the radius that DBSCAN uses to find neighbors. This means more points will be considered close enough to be grouped together, resulting in fewer, larger clusters. Imagine drawing bigger circles around each point. The circles will overlap more and merge clusters. I agree this is also true. A smaller EPS means you're making the radius smaller, making it harder for points to be grouped together. This will lead to more points being left out of any clusters and labeled as noise. Think of drawing tiny circles. Many points won't have enough neighbors within their tiny circles, so more will be labeled as outliers or noise. I believe this is true as well. By raising min_samples, I'm making it more difficult to form a cluster. It takes a higher density of points within the given radius to create a cluster. This makes fewer clusters overall, as the criteria for forming a group are stricter. It's like raising the bar. Fewer groups will meet the requirement. This is true also. I expect that lowering min_samples makes it easier to form a cluster, as fewer points are needed to satisfy the density condition. Therefore, fewer data points will be left ungrouped and labeled as noise. Think of lowering the bar for forming a group. More groups will satisfy the requirement, resulting in fewer ungrouped points or noise.